Welcome to All in All. Today we're embarking on an incredible journey, one that takes us right to the very edge of our solar system, to a realm that's, well, it's vast beyond imagination, profoundly mysterious, and yet surprisingly influential. We're diving deep into the Oort Cloud. Imagine, if you will, our sun, just a tiny speck at the heart of this enormous kind of ethereal bubble.
It's bubble, yeah.
A colossal spherical shell of icy objects, that's the Oort Cloud. It was first theorized by pioneering astronomers Ernst Öpik and Jan Oort. Their insights really laid the groundwork for understanding this distant frontier. But what exactly is this Oort Cloud? How did it get way out there? And maybe most importantly, why should we, down here on Earth, care about something that feels so incredibly remote?
Indeed, it's a truly fascinating concept, and one that holds really critical insights into the formation and, well, the ongoing dynamics of our entire solar system. While we haven't directly observed the Oort Cloud in its entirety, the indirect evidence for its existence is, frankly, incredibly compelling. This deep dive will explore not only its profound origins, but also why it holds such significance for us, how it's evolved over cosmic timescales, and even its surprising practical relevance for our future understanding and, exploration of the cosmos.
Okay. So settle in, because we're about to embark on a journey to unpack the secrets of the Oort Cloud. From its tumultuous icy formation billions of years ago to its surprising continuous impact on life and the very environment right here on Earth. This is where the universe truly shows us its intricate connections, even across unimaginable distances.
Yeah.
Okay, so to set the stage, let's begin by defining what we're actually looking at when we talk about the Oort Cloud. How far out are we really talking, and what's it composed of?
Well, okay, imagine our sun right at the very center of our solar system. Then zoom out, way out, past all 8 planets, past the gas giants, past Neptune, and even beyond the Kuiper Belt, that ring of icy objects where Pluto lives. The Oort Cloud is believed to begin at an astounding distance, roughly 50,000 astronomical units from the sun.
50,000 AU.
Yeah. And to put that in perspective, 1 astronomical unit, or AU, that's the average distance between the Earth and the sun, about 150 million kilometers, or 93 million miles. So 50,000 AU is 50,000 times that distance.
Wow.
And to truly grasp the scale, think about Voyager 1. Our furthest spacecraft launched back in the late 70s. Even after more than 45 years of continuous travel, Voyager 1 will still take approximately, get this, 300 more years just to enter the inner edge of the Oort Cloud.
300 years just to get there.
Exactly. And then it would take another maybe 30,000 years to fully exit its outer boundary. That gives you a sense of its immense, almost unfathomable scale.
30,000 years to pass through it.
Yeah.
That's not just immense. That's a time scale that almost breaks the human mind. And it's often described, isn't it, as marking the very boundary of our solar system, the place where our cosmic neighborhood truly ends.
Precisely. Yeah. It's considered to be the limit of the sun's dominant gravitational influence, a region often referred to as the Hill sphere. Beyond this point, the sun's gravitational pull isn't the sole overwhelming force anymore. The gravitational influence of the Milky Way galaxy itself, that vast spiral arm we call home, or even the subtle tug of passing stars, begins to take over. It starts to profoundly shape the orbits of objects out there. It's where the sun's kingdom gives way to galactic currents.
Right. So if it's this vast, distant region, what kind of objects are we talking about out there? Are they like mini planets or something else entirely?
They're predominantly small, icy bodies. Though small is relative here. They can range from just a few kilometers across to maybe tens or even hundreds of kilometers, essentially the size of mountains or even small moons. Their composition is largely volatile. Ices, think water ice, ammonia, methane, pretty much like the pristine building blocks that existed in the earliest days of our solar system.
Raw ingredients.
Exactly. And we estimate, based on models and, observations of comets, that there could be anywhere from hundreds of billions to a staggering 2 trillion of these objects. Though that number, it remains theoretical because, like we said, we haven't directly observed the cloud itself.
But that's the crucial question, isn't it? If we haven't actually seen this enormous structure directly, how do we know it's there? What's the concrete evidence for something so distant and, well, to our telescopes, seemingly invisible?
That's a fundamental point, yeah. And the evidence is quite compelling, though it is indirect. The primary support for the Oort Cloud's existence comes from observing specific types of comets that visit the inner solar system. The first category is what we call near parabolic comets, or more commonly, long-period comet.
Long period of comets, right.
These are comets with extremely elongated, almost parabolic elliptical orbits that bring them in from incredible distances. Their semi-major axes, that's half the long axis of their orbit, can range from, say, 1,000 to over 100,000 AU.
Huge orbits.
Massive. And the crucial insight here is that such incredibly elongated orbits strongly suggest an origin point in a vast, distant, spherical reservoir like the Oort Cloud. Rather than, say, a flattened disk like the Kuiper Belt, these are comets making their very first, or maybe only their second or third, journey into the inner solar system. They're fresh.
And there's also something called scattered disk objects, right? How do they fit into the picture? Are they part of the evidence too?
Yes, that's the second type of evidence. And they're often seen as a kind of transitional population between the Kuiper Belt and the Oort Cloud proper. Scattered disk objects are icy bodies whose maximum distance from the sun, their aphelion, extends beyond 2,000 AU. So they overlap significantly with the inner regions of what we predict for the Oort Cloud.
Okay.
The patterns of their orbits, and especially the ultra-long period or the hyperbolically orbiting comets we've detected.
Hyperbolic meaning they're on their way out. Or from outside.
Exactly. Either on their way out of the solar system forever,
Yeah.
or possibly interstellar visitors just passing through, but whose trajectories hint at origins at vast distances. All these provide robust, indirect observational reasons to believe the Oort Cloud is real. It's also, frankly, the most accepted scientific explanation for why comets continue to exist in an old solar system like ours.
Right, because otherwise they'd have just burned off.
Pretty much. If there wasn't such a distant, replenishing source, the inner solar system, baked by billions of years of solar radiation, would have cooked away and depleted all its comets long, long ago. So the ongoing appearance of these fresh comets is itself a powerful argument for the Oort Cloud's presence.
Yeah.
It has to be coming from somewhere.
That makes sense. It's like inferring a massive hidden iceberg just by the few chips that break off and float closer to shore.
Yeah.
But does relying so heavily on this indirect evidence, these chips off the iceberg, does that introduce any significant uncertainties? Or maybe debates among scientists about the Oort Cloud's true size or its structure or even its exact population?
Oh, that's an excellent point. And absolutely, yes, there are definitely ongoing debates. While the consensus for the Oort Cloud's existence is really strong, its precise characteristics remain subjects of active research and modeling. For example, the estimated number of objects that 2 trillion figure is a huge range, right? And the exact boundaries of its inner and outer edges, whether it's truly a uniform sphere or maybe has some underlying structure like a denser inner core and a sparser outer halo, these are all questions scientists are constantly trying to refine through more sophisticated modeling and, crucially, through new observations of every long-period comet we find.
So each new comet is like another clue.
Exactly. We're constantly working to piece together a more detailed picture, and each new long-period comet or unusual object, like, say, Sedna, adds another vital data point to that cosmic puzzle. It's a field where our understanding is, continuously evolving.
So we have this immense icy shell, this relic of the early solar system, inferred from the comets it sends our way. But how did it actually come to be? Was it always there, way out in the boonies, or did something create it, shape it into this distant reservoir?
Right. The formation of the Oort Cloud is a complex puzzle, but there are several leading theories, all really well supported by what we understand about the early, tumultuous dynamics of our solar system. The prevailing idea, the most widely accepted one, is that the objects now residing in the Oort Cloud actually originated much, much closer to the sun.
Closer in.
Yeah, within the primordial solar nebula itself. That was the vast, swirling disk of gas and dust from which all the planets, asteroids, and other small bodies in our solar system formed billions of years ago.
So essentially, not formed out there in the cold, distant reaches, but rather moved out there by some powerful mechanism.
Exactly. You can think of it like a cosmic diaspora, a massive migration. During the early chaotic phases of our solar system's formation, especially in the first few tens of millions of years, the giant planets Jupiter, Saturn, Uranus, and Neptune played a truly crucial and actually quite violent role.
The big bullies on the playground.
Kind of. Their immense gravitational influence acted like a series of cosmic slingshots. As these planetesimals and icy bodies were forming in the inner and outer regions of that protoplanetary disk, many had close encounters with these growing behemoths. The result was this dramatic scattering event. Vast numbers of these small icy bodies were flung out to the very fringes of the solar system, or even ejected entirely.
Ejected completely, like gone from the solar system.
Yeah. It's estimated that something on the order of maybe 99% of the original small bodies, the building blocks of planets, were actually kicked out of the solar system completely. They're now just wandering the galaxy as free-floating interstellar objects. Rogue planets, rogue asteroids, rogue comets.
Wow, 99%.
It was incredibly inefficient. The remaining ones, though, the lucky few percent that received a very precise, sort of carefully calibrated gravitational nudge from the giant planets, ended up in these distant, highly eccentric, but just stable enough orbits, and those now form the Oort Cloud.
That's an incredibly violent origin story. Just planetary billiards on a massive scale. But I've also heard something intriguing about material being captured from other stars during our sun's formation. How does that fit in? Could some of our Oort Cloud objects actually be like interstellar immigrants?
That's a fascinating and increasingly plausible alternative theory. Or maybe it's complementary, not necessarily either.
Right.
It suggests that while our sun was forming within a dense stellar nursery, a cluster of thousands of newly born stars all kind of huddled together, it might have gravitationally captured cometary material from the outer disks of other stars forming in the same nebula.
Like swapping spit, cosmically speaking.
Yeah. Huh. Something like that. A cosmic exchange program. In such a dense stellar environment, stars often pass relatively close to one another, and their nascent planetary disks can gravitationally interact. They can literally steal material from each other. So it's entirely possible that some of the objects we now call our own in the Oort Cloud could actually be interstellar immigrants. Cosmic souvenirs from our sun's birthplace, captured from a neighboring stellar system during those chaotic formative years.
And this is where the puzzle pieces start to connect in really unexpected ways.
Yeah.
Because there was that truly surprising recent discovery you mentioned earlier, inner solar system material found in the Oort Cloud. How does that work? Isn't the Oort Cloud supposed to be made of icy stuff flung from the outer system? This sounds like it fundamentally challenges that basic idea.
You're touching on one of the most exciting recent developments. Yeah, it really shook things up a bit. This was a truly surprising discovery related to a comet designated C2014 S3 Pan-STARRS. It got nicknamed the Manx Comet.
Like the tailless cat.
Exactly, because it had very little cometary activity, very little tail or coma. What made it unique and so surprising was its spectral reflectivity. That's essentially how the comet reflects sunlight, which acts like a fingerprint of its chemical composition.
Okay.
Its reflectivity was consistent with S-type asteroids. And S-types are primarily found way closer in the inner asteroid belt.
Near Mars and Jupiter.
Right. And crucially, S-type asteroids are composed predominantly of rocky silicate material, not the volatile ices like most comets. So we had a comet clearly coming from the Oort Cloud based on its orbit that looked, well, rocky. Not icy.
That really does flip our assumptions on their head. How on earth did a rocky inner solar system object get flung all the way out there, only to come back in looking like a comet?
Well, the leading hypothesis now is that this inner solar system material was also flung out by those same gravitational interactions of the giant planets during that same early, unstable period of planet formation.
So the slingshot worked both ways. Inner and outer stuff got tossed.
It seems so. But rather than being entirely ejected from the solar system, or maybe settling into the Kuiper Belt, this particular rocky stuff received a gravitational kick that sent it all the way out to the Oort Cloud. And the key insight here, what made scientists still classify it as a comet, despite its rockiness, was its dust coma. Observations during its passage near the sun showed continuous activity, a consistent release of dust, not just like a one-off impact or a brief burst from ice hitting sunlight for the first time.
So it was still active like a comet, even if it was rocky.
Exactly. This continuous activity indicated it was indeed behaving like a true comet, despite its unusual composition. This discovery wasn't just a fascinating anomaly, it fundamentally challenged that neat compartmentalization we had of the early solar system: rocks stay in, ice goes out. It suggests the mixing pot was far more agitated than we maybe imagined. It's forced planetary scientists to reevaluate how material was distributed and even question our assumptions about the origins of other rocky bodies we thought were purely inner solar system products. It shows how one peculiar comet can potentially unravel a whole chapter of cosmic history we thought we understood.
So we're talking about a kind of cosmic lost and found system, or maybe return to sender, where material from our own inner system got bounced all the way out to the Oort Cloud. And now, billions of years later, some of it is finding its way back. That paints a remarkable picture of a solar system that was far more turbulent and dynamic in its youth than we often imagine. But this isn't just a static collection of ancient ice and misplaced rocks. The Oort cloud isn't just sitting there idly, is it? It's constantly evolving, interacting with its environment. What's happening out there at the edge of our solar system over these vast stretches of time?
That's absolutely right. Despite its immense distance, the Oort cloud is far from static. It's a dynamic place. Its objects are subject to significant and continuous external influences. One of the most important is the galactic tidal field.
Galactic tides. Like ocean tides, but from the whole Milky Way.
Sort of, yeah. It's the subtle but persistent gravitational pull exerted by the rest of the Milky Way galaxy, the galactic center, the spiral arms, all that mass on our solar system. You can imagine the entire galaxy acting like a giant invisible hand, subtly stretching and squeezing the Oort cloud over billions of years. This pull subtly but continuously reshapes the orbits of Oort cloud objects, leading to a process known as kinematic heating.
Kinematic heating. That sounds almost like a slow-motion unraveling. What exactly does it lead to for these distant, icy bodies?
Well, over incredibly long timescales, this relentless galactic tidal field, combined with occasional close encounters with passing stars, which we'll get to, causes the Oort cloud to gradually evaporate. Now, this isn't literal evaporation like water boiling away.
Right.
It means objects are gaining enough kinetic energy from these cumulative gravitational nudges that they are either sent hurtling into the inner solar system, becoming the long-period comets we see, or, actually more often, they're flung out into deep interstellar space entirely.
Becoming those interstellar objects like Oumuamua.
Exactly like Oumuamua and Borisov. These lost objects, having gained enough energy from these perturbations, become free-floating interstellar asteroids or comets, possibly originating from other Oort cloud-like structures around other stars. In fact, because of these relentless forces, the Oort cloud is estimated to have a half-life of about 1 billion years.
A billion years, so half of it is gone every billion years?
Roughly, yes. It means that approximately half of its original population will have been lost or ejected over that period. It really highlights its dynamic, non-static nature. It's constantly shedding material.
Okay, speaking of passing stars, what happens when another star gets close to our Oort cloud? Does it just, calmly pass by, or is there a more dramatic effect?
Oh, far from it. These stellar encounters are a major source of perturbation, and they are anything but calm. Even a relatively distant pass, where a star doesn't directly plow through the densest inner Oort cloud, can have really dramatic gravitational effects. When a star passes within the Oort cloud, its gravity perturbs the orbits of countless icy bodies. Many are indeed flung out into deep space, joining those interstellar wanderers we just talked about. But many others are sent hurtling towards the inner solar system on new, highly eccentric paths.
And that leads to?
That can lead to what's famously known as a comet storm, a significant, measurable increase in the rate of comets entering the inner solar system over a period of time.
A comet storm. That sounds dramatic.
And frankly, a bit terrifying if you're thinking about impacts. Has anything like this happened before, or is it something we only need to worry about in the extremely distant future? It has absolutely happened before. And crucially, the effects of a major past event are still unfolding and will continue to impact our distant future. Approximately 70,000 years ago, which is like yesterday, cosmically speaking, a faint binary system known as Schultz's star passed incredibly close to our sun.
Schultz's star? What kind of stars are there?
It's a small red dwarf and an even smaller brown dwarf companion. Very faint, not something you'd notice in the sky. But it passed within about 52,000 AU of the sun. That's definitively within the Oort cloud, probably even the denser inner parts of it.
Okay, so right through the thick of it.
Pretty much. And this close passage, which we know about through really precise astrometric measurements of its past trajectory, likely perturbed thousands upon thousands of large Oort cloud objects. We're talking things typically 1 kilometer or larger in size.
And the impact of that event. Have we felt that already, or is it still like a cosmic time delay fuse burning?
It's very much a cosmic time delay fuse. We are definitely still waiting for the full effects to be felt. You see, the perturbed comets are on such long, slow orbits that it takes vast amounts of time, often millions of years, for them to travel inward towards the sun after being nudged.
Right, it's not instantaneous.
Not at all. It's anticipated that around 2 million years from now, give or take, over a window spanning maybe tens of thousands of years, we will experience a significant increase in the number of comets plunging through our inner solar system, all because of this single past encounter with Schultz's star 70,000 years ago.
2 million years from now.
Yeah. The full repercussions of that ancient stellar flyby are still very much to come. It's a compelling example of these deep-time astronomical effects playing out.
So a cosmic time bomb set tens of thousands of years ago, with the effects only arriving in the deep future. That's truly mind-boggling to consider.
Are there any other stars on a trajectory that we know of that are predicted to impact our Oort cloud in the, foreseeable future? Million-year timescale foreseeable. Yes, actually. Another notable example is Gliese 710. It's a relatively common K-type star, a bit smaller and cooler than our Sun. This star is predicted to pass through the Oort cloud at a distance of about 0.06 light-years. That translates to roughly 3,800 AU.
That sounds even closer than Schultz's star went.
Potentially much closer to the Sun, yeah. A very close shave, astronomically speaking, and deep within the Oort cloud's estimated boundaries. This close encounter is expected to occur in approximately 1.3 million years.
Okay.
And like Schultz's star, it will inevitably disturb countless comets as it passes through. It'll send many hurtling towards the inner solar system, potentially initiating another, possibly even stronger wave of increased cometary activity. And these aren't just theoretical possibilities, right? These are predictions based on robust astrometric data, especially from incredible missions like the European Space Agency's Gaia satellite.
Gaia, which maps the stars with incredible precision.
Exactly. Gaia precisely maps the positions and motions of billions of stars in our galaxy, allowing us to calculate these past and future close encounters with remarkable accuracy.
Given all this chaos and perturbation, then from galactic tides constantly nudging things, to these passing stars delivering major jolts, how stable are objects within the Oort cloud? And maybe zooming out, how stable is the wider solar system over these incredibly long timescales? It sounds like a pretty delicate balance out there.
This raises a truly important question, yeah. The long-term stability of orbital mechanics, it's a whole field that grapples with predicting the future of celestial bodies over billions of years. Scientists use complex mathematical models to understand these intricate dynamics. They often involve concepts like Hamiltonian systems and perturbation theory.
Okay, Hamiltonian systems, perturbation theory. Can you break those down a bit?
Sure. Think of Hamiltonian systems as basically a mathematical way to describe the total energy kinetic plus potential of a gravitational system like the Oort cloud or our entire solar system in a really concise form. This makes it easier to track how that energy changes over time due to various forces.
Yeah.
And perturbation theory is the sophisticated mathematical toolkit we use to calculate how tiny external gravitational nudges, these perturbations from the galaxy or passing stars, accumulate over billions of years to subtly yet profoundly reshape the orbits of these distant icy bodies.
So it's about tracking the energy in the small nudges over eons.
Precisely. And while even our inner planets like Mercury and Mars show some chaotic behavior in their orbits over millions of years due to complex gravitational resonances with each other, and Jupiter, the Oort cloud objects are particularly susceptible to these external influences. Because they're so far out, their gravitational ties to the sun are much weaker, so their orbits can undergo really significant changes due to relatively small nudges from outside forces. They're much less stable in the long run than the inner planets.
And what about the comets themselves? Once they do get nudged into the inner solar system and start that long journey towards the sun, do they last forever? Or do they have a finite lifespan?
Oh, not at all. In fact, Jan Oort himself noticed this back in the day. Many long-period comets simply seem to disappear after only a few passes through the inner solar system. They don't keep coming back forever.
They just vanish.
Pretty much. Once these icy bodies are sent inward, they get exposed to the sun's increasing heat and radiation. This causes them to sublimate, that's where the ice turns directly into gas and dust, bypassing the liquid state, and they lose significant amounts of material with each pass by the sun.
It's like a cosmic ice cube melting away each time it gets near the fire.
That's a perfect analogy. Comet Ison back in 2013 was a classic, maybe disappointing example. It came a long, long way from the Oort cloud, was hyped up to be a magnificent spectacle, maybe the comet of the century.
I remember that one.
But it largely disintegrated as it got really close to the sun. It offered only a brief and faint display before vanishing completely. So only a very few of these long-period comets actually survive enough passes to revisit the inner solar system multiple times, which is exactly why we constantly need new ones to appear, delivered fresh from the Oort cloud reservoir.
Okay, so moving beyond just being this distant icy shell and sort of comet factory, what's the real significance of the Oort cloud? Why does it matter to us here on Earth beyond just being a fascinating astronomical concept?
Its significance is actually truly profound. It touches on everything from the very origins of our planet's water to the potential for future cosmic events that could, shape Earth's environment. First and foremost, as we've said, it's the primary reservoir for long-period comets, those with orbital paths over 200 years. Without the Oort cloud continuously replenishing the inner solar system with these fresh icy bodies, our cosmic neighborhood would likely be pretty much devoid of new cometary visitors. Any comets formed closer in would have long since sublimated away or been ejected. It's a vital, ongoing supply.
And those cometary visitors, as we touched on with comet storms, they can potentially be dangerous, right?
Mm-hmm.
What's the potential impact of a comet collision compared to, say, an asteroid? Is one inherently more threatening than the other?
That's a critical distinction to make, yeah. Studies generally suggest that for the same mass, a comet impact would likely result in significantly more damage to Earth.
More damage, why?
Potentially as much as 10 times the devastation compared with an asteroid of the same size. This is mainly due to two factors. First, they're generally higher velocities. When they enter the inner solar system, they're falling from much further away, so they pick up more speed.
More kinetic energy.
Exactly. And second, they're different compositions. They're often less dense, but contain more volatile materials, which can lead to larger atmospheric disruptions, bigger air bursts, and potentially more widespread environmental effects upon impact compared to a solid rock. Now, while the current consensus for the dinosaur extinction event 65 million years ago points firmly to an asteroid impact,
The Chicxulub impactor.
right, the potential for future cometary impacts from the Oort cloud, especially during one of those predicted comet storms triggered by a passing star, remains a significant, albeit thankfully very low probability, concern for Earth. It's a reminder that even these very distant phenomena can potentially have direct consequences for our planet.
Definitely food for thought.
Yeah.
This also raises that really important and long-standing question in planetary science.
Yeah.
Where did Earth's water come from? Our planet is, uniquely watery in the inner solar system. Could the Oort cloud have played a role in delivering it?
That is indeed a huge and ongoing debate, one that directly connects us to the Oort cloud and the early solar system. Researchers generally agree that Earth's water was likely delivered by small bodies after its initial formation, which probably left it as a largely dry, molten rock.
So it wasn't baked in from the start.
Probably not most of it, no. The leading contenders for these water delivery mechanisms are basically threefold: asteroid-like bodies from the region of Jupiter, Oort cloud comets, and Kuiper belt comets. The key to unraveling this mystery lies in analyzing the isotopic flavor of water, specifically the ratio of deuterium to hydrogen.
Deuterium. That's heavy hydrogen, right?
Exactly. Deuterium is an isotope of hydrogen, meaning it has an extra neutron in its nucleus. This D to H ratio acts like a unique chemical fingerprint. It helps scientists trace the origin of water across the solar system because different regions of the original solar nebula are thought to have had different deuterium to hydrogen ratios based on temperature and other conditions.
Okay, so compare the DDH ratio in Earth's oceans to the ratios in asteroids and comets.
Precisely. And what has the groundbreaking Rosetta mission told us about this particular isotopic flavor and the origin of Earth's water?
Rosetta visited Comet 67P, right, which is a Kuiper belt object, not strictly Oort cloud.
That's correct. Comet 67P Churyumov-Gerasimenko is a Jupiter family comet, which means its orbit is primarily controlled by Jupiter, and it's thought to originate in the Kuiper belt, or the scattered disk, not the distant Oort cloud. But the key here was the Rosina instrument aboard Rosetta. Rosina is essentially a highly sensitive mass spectrometer. Think of it like a cosmic taste tester for the gases erupting from the comet's nucleus. It precisely measured the isotopic flavor, the D to H ratio, of the water vapor coming off Comet 67P.
And the result?
The result was quite surprising at the time. It found that 67P's water had a significantly different deuterium to hydrogen ratio than Earth's oceans. Much higher, actually.
And not a match.
Not a match for that specific comet, no. Now, this finding, while crucial, isn't definitive for all comets, whether from the Kuiper belt or the Oort cloud. Comets show a surprising diversity in their D to H ratios, but it certainly complicated the simple idea that comets were the sole or even primary source of Earth's water. In fact, this particular result, combined with measurements from some asteroids that do match Earth's water better, actually lends more support to models suggesting that asteroids, perhaps from the outer asteroid belt near Jupiter, were the main delivery mechanism for Earth's vast oceans. Or maybe it was a mix of sources.
So the jury's still out, but Rosetta shifted the balance a bit.
It absolutely did. It's a testament to how one incredibly detailed mission to just one small body can profoundly shift our understanding of planetary origins.
It really is almost like the Oort cloud acts as a kind of geological record keeper for the early solar system.
Yeah.
Holding these pristine, ancient clues to our own origins, it's truly a cosmic time capsule out there.
Absolutely. And speaking of peculiar objects and cosmic time capsules, another significant aspect and a very peculiar object indeed is Sedna.
Ah, yes, Sedna, discovered back in 2003, right?
That's right. Sedna is a dwarf planet candidate, a planetoid thought to originate from the inner Oort Cloud, or maybe a region just beyond the main Kuiper belt, sometimes called the detached disk. It has this highly eccentric orbit, a very stretched out ellipse. Its closest approach to the Sun, its perihelion is way out at 76 AU.
76 AU, that's more than twice Neptune's distance.
Exactly. And its farthest point, its aphelion, is way out around 900 AU, deep into what we think of as the inner Oort Cloud region. And its orbit takes roughly 11,400 years to complete.
11,000 years.
Yeah.
What's so special about Sedna's orbit, though? Why is it considered so peculiar, and why does it suggest something unique about the Oort Cloud or beyond?
What's truly fascinating and puzzling is that Sedna's orbit never brings it close enough to any of the known major planets, not even Neptune, for their gravity to have plausibly scattered it out there onto its current path.
So Neptune couldn't have kicked it out there.
Not onto that specific orbit, no. Current models suggest Neptune's influence doesn't reach strongly enough to lift Sedna's perihelion that high to 76 AU. This orbital isolation suggests a unique formation or placement mechanism. It's detached from the gravitational influence of the giant planets.
Well, what could have put it there?
That's the big question. Scientists are still asking critical questions about Sedna. Its exact origin, was it scattered out by an unknown, perhaps Mars-to-Earth-sized Planet 9 lurking in the distant solar system? That's one leading theory. Or perhaps was it captured from a passing star during the Sun's birth in that stellar cluster we talked about? Or maybe perturbed by a star that passed closer than Schultz's star long ago?
Lots of possibilities.
Exactly. And we also want to know its precise composition compared to Kuiper belt objects. Is it truly distinct? Does it contain even more pristine primordial material from the earliest solar system? We also want to understand its geophysical properties. Is it geologically active? Does it have cryovolcanoes like Pluto? Does it have satellites or even a tenuous atmosphere when it's closer to the sun?
And we have a limited time to study it, right? Since it's heading back out.
That's the urgency. Since it won't be back to its perihelion, its closest approach for over 10,000 years, studying it now while it's relatively close to the sun, around 80-something AU currently, is incredibly crucial. It represents our best chance for potentially millennia to understand the objects in these earliest, most distant regions of our solar system, regions otherwise inaccessible.
Fascinating. And what about other hypothetical objects that might be out there lurking in the Oort Cloud? For years, we've heard whispers of Planet X, or as you mentioned, Planet 9, or even something more exotic. What does the Oort Cloud tell us about these possibilities? Or does it just provide a good hiding place?
Well, the Oort Cloud has certainly been a proposed hiding place for various hypothetical objects, mainly because it's so vast and distant, making detection incredibly difficult. For instance, there was the hypothetical gas giant Taish, proposed back in 1999.
Taish, right. What was the idea there?
Its existence was speculated based on a supposed statistical bias, a pattern, in the origin points of long-period comets coming from the Oort Cloud. The idea was that a large undiscovered planet's gravitational influence out there was subtly hurting them, creating this pattern.
Makes sense. Did they find it?
No. Data collected by NASA's Wide Field Infrared Survey Explorer-WISE back in 2014 conclusively ruled out any object with Taish's proposed characteristics. WISE was an infrared space telescope, perfect for detecting large, cold objects like gas giants, even far from the sun. If a Neptune-sized or Jupiter-sized gas giant like Taish had been out there in the Oort Cloud, WISE would almost certainly have seen its faint infrared glow.
Okay, so scratch tight.
Scratch Taish as a gas giant in the Oort Cloud, yes.
But what about the more recent and maybe more scientifically plausible idea of Planet 9? Not necessarily a gas giant, maybe smaller, and potentially responsible for Sedna and other detached objects. And then there's that really speculative idea. Could Planet 9, if it exists, actually be a black hole? It sounds like something straight out of science fiction.
It does sound like science fiction, but it's an idea that has indeed been seriously explored by some theoretical researchers. It's highly speculative, mind you, but intriguing.
How would that even work?
Well, the possibility they investigated is that Planet 9, if it truly exists and is responsible for the observed clustering of certain distant Kuiper belt objects, might not be a planet in the traditional sense at all. It might instead be a primordial black hole.
Primordial, meaning from the Big Bang.
Exactly. A small, ancient black hole formed in the chaos of the very early universe, potentially only about the size of a grapefruit, but still having several times the mass of Earth. In this highly theoretical scenario, its existence could potentially be discovered not by seeing the black hole itself, which would be incredibly difficult, if not impossible, at those distances, but indirectly,
Oh.
by a powerful new observatory, the Vera C. Rubin Observatory, currently under construction. Its Legacy Survey of Space and Time, LSST, will repeatedly scan the sky. The idea is that the LSST could detect brief accretion flares, little bursts of energy, essentially light, caused by small Oort Cloud objects or other distant icy bodies, occasionally falling into this hypothetical primordial black hole, Planet 9.
Like a cosmic death cry.
Kind of, a flash of light as material gets superheated falling in. The theoretical detection rate for such an event, if Planet 9 is a black hole of about 5 Earth masses, would be maybe a few such flares per year across the whole sky survey. So this method could potentially detect or maybe even rule out primordial black holes of that mass range out to distances of maybe 100,000 AU well into the Oort Cloud.
That would be incredible. Indirect evidence, but still.
Absolutely. It would be indirect evidence relying on these fiery, fleeting events to reveal a hidden, massive gravitational presence. It really pushes the boundaries of discovery and our understanding of what might really be lurking in the deep, dark reaches of our solar system.
It's incredible to think about the possibilities, even the most theoretical ones, that lie hidden in that vastness. Now, we've talked about how incredibly far away the Oort Cloud is and how long it would take for even our fastest spacecraft like Voyager to just enter its inner edge. Does humanity have any real concrete plans, any missions on the books to actually explore this distant region with a dedicated mission?
Well, currently, there's no specific funded timeline for a dedicated full-scale mission to the Oort Cloud itself. It remains an incredibly complex and challenging area of research, primarily due to those immense distances, the sheer vastness of the region itself, and the extremely faint and sparse nature of its individual objects. It's like finding needles in a cosmic haystack the size of a solar system.
So it's just too hard right now.
Pretty much. We need to learn much more first through advanced telescopes, both ground-based like Rubin and space-based like Webb, and through better gravitational modeling and sophisticated simulations of its formation and evolution. Only then can we seriously consider sending a spacecraft specifically there. And the technology required for such a mission, especially for anything beyond just a rapid flyby, would be formidable. We'd need advanced propulsion systems way beyond what we have now, and long-duration power sources that could last for centuries. That's still likely decades, if not centuries, away from being fully realized.
But despite those huge challenges, there have been some preliminary proposals or ambitious ideas over the years, haven't there? People have certainly dreamed about reaching that far.
Oh, indeed. The dream of reaching the outer limits of our solar system has long captivated scientists and engineers. Back in 1987, for instance, the 1,000 Astronomical Units, or TAU, probe was proposed.
TAU. What was that about?
It was a really ambitious concept specifically designed to study the outer solar system and the interstellar medium beyond the heliopause. It aimed for distances far beyond the known planets, potentially reaching 1,000 AU or more, which would put it well on the way towards the inner Oort Cloud region. It envisioned using advanced propulsion like nuclear electric power.
Ambitious for the 80s.
Very. And later, around the 2010s, the Whipple mission was suggested. This mission concept took a different approach. It aimed to search for both Kuiper Belt objects and potential Oort Cloud objects by looking for their occultations.
Occultations, like eclipses.
Exactly. Where they pass in front of distant stars, briefly dimming their light. Whipple would have stared at star fields, looking for these tiny, brief dips in brightness as faint, distant objects passed by. It was a clever way to detect objects too faint to see directly. However, Whipple ultimately wasn't selected for NASA's Discovery program. It highlights the significant investment and the formidable technological hurdles these kinds of far-reaching missions still face. They're competing against missions to targets much closer and easier to reach.
Makes sense. So, okay, if we were to send a mission out towards the Oort Cloud region relatively soon, maybe not to the main cloud, but towards its inner edges, given current technological capabilities and the incredible distances, what would be the most promising and scientifically compelling immediate target?
Without a doubt, I think the consensus would be Sedna.
Sedna again.
Yeah.
Because it's coming relatively close right now.
Exactly. As we discussed, its highly eccentric orbit means it spends the vast majority of its 11,400-year journey incredibly far from the sun, deep in the cold. It won't return to its closest approach, its perihelion at 76 AU, for over 10,000 years. This means a mission to intercept it while it's relatively close to the sun, which it is now, in the 80-something AU range would need to be planned pretty much now for a launch around, say, 2033 or maybe 2040, depending on the trajectory. We need to capitalize on its current proximity.
So there's a window of opportunity.
A very long, slow window. But yes, Sedna represents potentially the largest and certainly the most accessible inner Oort cloud candidate or detached disk object that we'll have a chance to study up close for literally millennia. Understanding Sedna could unlock unprecedented secrets about the inner Oort cloud, the processes that shaped the earliest solar system, and maybe even give us clues about the existence or absence of that potential Planet 9. It's a unique scientific prize.
Okay, shifting gears slightly. Beyond pure scientific curiosity, which is certainly compelling enough for many of us, does the Oort cloud hold any practical relevance for humanity's future? Could it, perhaps, crazy as it sounds, be a resource for future space exploration? Mining the Oort cloud.
This raises a really important question, and it's where we connect this distant, icy realm to the bigger picture of long-term space exploration and maybe humanity's future out in the cosmos. The icy trans-Neptunian objects, including those that are thought to populate the Oort cloud, are believed to contain significant amounts of water ice, obviously, but also ammonia and various carbon-rich compounds.
The building blocks of life, essentially.
Pretty much. The basic ingredients for life and perhaps more practically for sustaining humans or robotic missions during long-duration space travel. Think water for drinking, oxygen for breathing, maybe even soil for growing things if processed correctly. And crucially, modeling suggests they may also hold significant amounts of rare and potentially valuable isotopes like deuterium and helium-3.
Deuterium and helium-3, and these are valuable for what specific applications? How could they fuel our future endeavors?
Well, deuterium, as we mentioned, is heavy hydrogen. It could be a critical fuel for future deuterium or deuterium-tritium fusion rockets.
Fusion rockets, like Star Trek stuff.
Kind of. Fusion potentially offers a much, much more powerful and efficient propulsion method than chemical rockets or even the ion engines we use today. It could dramatically shorten travel times across the solar system and maybe even enable interstellar travel. And helium-3 is another isotope, rare on Earth, but thought to be more abundant in the outer solar system and potentially on the moon. That's considered a prime fuel for certain types of cleaner fusion reactions, ones that produce fewer neutrons.
Okay, so rocket fuel. But how would you get it from the Oort cloud?
This leads to the really long-term, highly theoretical concept of self-replenishing fusion rockets, or interstellar refueling stations. Imagine spacecraft, maybe centuries from now, that could stop at, say, a 10-kilometer-wide Oort cloud object, effectively a cosmic iceberg, and mine the necessary isotopes, like deuterium from the water ice, directly from these icy bodies. They'd refuel in deep space.
Wow, cosmic filling stations.
Exactly. This is still highly theoretical, of course. It requires huge technological advancements in both fusion power generation for spacecraft and in in-situ resource utilization, basically, mining and processing materials in space on these small, cold bodies. But it highlights the potential for these distant icy bodies to be more than just a source of pretty comets or scientific curiosities. They could, theoretically, enable true interstellar travel, where you hop from one Oort cloud object to the next, mining resources along the way to gradually reach other star systems, extending humanity's reach far, far beyond our own sun.
That is a mind-bending prospect. So, wrapping this all up, what does this all mean for our long-term understanding and our future in the cosmos? It truly sounds like the Oort cloud is not just an ending, the edge of the solar system, but potentially a beginning.
I think that's a great way to put it. The Oort cloud really stands as this profound testament to the dynamic and still unfolding history of our solar system. It reminds us very powerfully that our cosmic home extends far, far beyond the familiar planets and even the Kuiper Belt. It reaches into this vast icy realm shaped by both our sun's ancient, chaotic past and those subtle, continuous gravitational whispers from the galaxy itself. It's a place where the deepest secrets of planetary formation, maybe the origins of Earth's water, and the potential for future cosmic encounters, both potentially devastating comet storms and perhaps resource-rich opportunities, are held frozen in literally trillions of icy fragments. It's a stark reminder that even the most distant corners of our solar system are deeply intertwined with our own story, our past, and potentially our future.
And perhaps then, in the very distant future, the Oort cloud won't just be the theoretical edge of our home system, but the very stepping stone to new frontiers. It's a truly compelling thought, isn't it? That these icy remnants kicked out by our giant planets billions of years ago might one day not only teach us more about our origins, but could actually fuel humanity's ambitious journey out to the stars. The deeper we dive into these distant mysteries, the more we truly understand our own place in the grand ongoing cosmic narrative. It's humbling, really. Thanks for listening to All I Know.